in the second lecture of this first week, we will talk more about vectors. We will talk about vector operations, we will talk about vector products, and then we will also talk about generalized vector spaces. Okay. And just to recap, so in the first lecture we talked about the basics of vectors. Okay. So, we talked about what are vectors, okay. We talked about vector spaces, and we talked about linear independence of vectors. So, we talked about vector spaces, linear independence, we talked about the concepts of basis and dimensionality. Okay. Now let us look at some other vector operations. Okay. Now, before we do that, let me mention a few vectors that you are familiar with from classical mechanics. Okay. So, for example, you are familiar with the position vector. So, the position of a particle r. Okay. So, the position r, okay, this represents the position of a particle, and it might be a function of time. So, r of t. So, position of a particle at time t. So, this is a well known example of a vector that you might have encountered in classical mechanics. Okay. You have also seen vectors like the velocity vector. So, the velocity of a particle v at time t, and what is interesting is that this is nothing but dr by dt. This is a time derivative of r, okay. And the time derivative of r is just given by dx by dt and dy by dt. So, it is a vector where each of the components are time derivatives of these vectors, and just to emphasize, your vector r is, in this case it is x of t, y of t, z of t in 3D space. Okay. So, if you are in 3D space, then the position vector r is written as it has 3 components x, y and t, z, and each of them are time dependent. So, they are functions of time. Now, the velocity, okay, is just a time derivative of the position. So, it has components, okay, which are just time derivatives, and you can write this these components, you might denote them as the x component of the velocity. This is also a function of time, y component of velocity, and z component of velocity, v z of t. Okay. So, you have seen things like position vector, velocity vector, you can have acceleration, which is a vector, you can have force, which is a vector, and so on. Okay. So, these are vectors are something that you have been seeing in classical mechanics for a long time, and they are also seen in different branches of physics and chemistry. So, now when we talk about operations on vectors, okay, so the vector space is defined, vector space is defined by 2 operations, namely addition and scalar multiplication. So, we know that if you add 2 vectors, you will get another vector, and if you multiply a vector by a scalar, you will get another vector. So, addition and scalar multiplication are necessary to define the vector space. So, you have to know how to add vectors, you have to know how to multiply them by a scalar. Now, there are other operations you can define, and these are additional things that you define on the vector space. For example, there is one operation called dot product or inner product product. Okay. So, what you do is you define the dot product or inner product of 2 vectors. Okay. Now, suppose you have 2 vectors r 1, which is denoted by x 1, y 1, z 1, and r 2, which is denoted by x 2, y 2, z 2. Then the dot product r 1 dot r 2, okay, this is a scalar. So, this is a scalar, this is a scalar, okay, and which is equal to x 1 times x 2 plus y 1 times y 2 plus z 1 times z 2. So, this is the usual, this is the definition of the dot product. It is also referred to as inner product. So, dot product or inner product. Okay. And this is how you usually define it in 2D or 3D space. Okay. And this is I should emphasize that this is not the only definition of the dot product. There can be other definitions of the dot product, okay, which I will not go into. I will not go into. There is a formal meaning of what can constitute an inner product. Okay. So, so a dot product or an inner product should satisfy two conditions. Okay, I'm writing the two main conditions. Okay, there are other conditions which I am not writing here. Okay, so the two important conditions that they should satisfy is that A dot B. So, if you take two vectors A and B and you take the inner product the dot product. So, this should be equal to B dot A, and A dot A is always, if you take an inner product of a vector with itself, okay, then it should always be greater than or equal to 0. Okay. In fact, it is equal to 0 only if A equal to 0. Okay, it is greater than or equal to 0 and it is equal to 0 only if A equal to 0. So, if these two conditions are satisfied, okay, then you can define an inner product in any way that these two are satisfied. Okay. So, this usual way of taking the inner product just by multiplying it component wise and adding up is just one way of taking an inner product, okay, but there can be other ways of taking the inner product. So long as they satisfy this rule, then it is a valid inner product. Okay. So, I won't talk, I won't speak more about the dot product. I will come back to this dot product or inner product when we are talking about generalized vector space, but I will just emphasize that vector space with inner product is called an inner product space. Okay. So, this inner product space is a kind of vector space that where the inner product is defined. You could have vector spaces where no inner product is defined, that is perfectly fine. You could have vector space where dot product is not defined. Vector space is defined only by addition and scalar multiplication. Okay. But if you have a vector space where an inner product is also defined which satisfies these conditions, okay, then it is called an inner product space. Okay. So, now there can be other kinds of vector products that are also defined, okay, and you could also define things like cross products, cross product of two vectors. Okay. So, so if you had two vectors, let us say R1 cross R2, okay, this is actually the cross product is unique to 3D. You cannot define a cross product in 2D in two dimensional space. Okay. So, if you had two vectors R1 and R2 in 3D, then you can define a cross product and you know how to define the usual cross product. So, if R1 has components x1, y1, z1 and R2 has components x2, y2, z2, then you write this as a determinant I j k, okay, and you write the components x1, y1, z1, x2, y2, z2. So, you write this in this form and this is a vector. So, this gives a vector. So, I can write it as I into y1 z2 minus y2 z1 plus j into z1 x2 minus x1 z2 plus k into x1 y2 minus x2 y1. Okay. So, this is the cross product, okay, and clearly it is a vector. So, the cross product of two vectors gives you another vector. Okay. So, we saw that the dot product of two vectors gives you a scalar, the cross product of two vectors gives you another vector. Okay. And you can also have other kinds of products, these are not the only kind of products. Okay. You can also define many different products of vectors. So, for example, suppose you had you can define something called a direct product. Okay. So, the direct product, and I will just use a notation. So, suppose you had the same two vectors r1 and r2, okay, then r1 you take a direct product with r2. Okay. Now, this I will denote it by a matrix. So, I will just show it as a matrix. Okay, I will show it in the matrix notation. So, what I do is I take x1 and I take, so let us write this in matrix form. So, suppose you had x1 y1 z1 and you take a direct product with x2 y2 z2. Okay. So, notice I have denoted r1 and r2 as column vectors. Okay. Then the result of this direct product is an object called a tensor, okay, which can be represented in a matrix form. So, x1 x2 x1 y2 x1 z2 y1 x2 y1 y2 y1 z2 z1 x2 z1 y2 z1 z2. Okay. So, I can represent this by a matrix. So, notice what I have done is I have taken x1 and I have multiplied it by x2, I have multiplied it by y2, I have multiplied it by z2, and I have taken all these products. Okay. Unlike in the cross product where I took suitable combinations of these products, here I kept all the 9 products. Okay. So, what I get is a 9-dimensional object, and this is a tensor. This is actually a tensor. Okay. I mean tensors are again quite important in for example, these play a role in time dependent perturbation theory. So, for example, or you can see in nonlinear response to external field. Okay. So, for example, you can have something called a polarizability tensor. So, for example, if you take a molecule and you put it in a strong electric field, okay, then if the molecule may not have its own dipole moment, but it might get polarized due to the electric field, and due to this polarization of the molecule it might induce a dipole moment. Okay. So, the tendency of a molecule to get polarized is represented by a tensor called the polarizability tensor. Okay. So, this is one place where you will see tensors appearing. Okay. So, for example, this plays a role in Raman spectroscopy. So, I mean you will see tensors in advanced quantum mechanics and spectroscopy courses. Okay. But what I wanted to emphasize through this is that it is not vector products can be defined in many different ways. Okay. There is no unique way of multiplying vectors, okay, but you can define several different ways to multiply vectors. Okay. Now, next I want to generalize the idea of vector spaces. Okay. So, we have seen 2D and 3D vector spaces. Now, we can easily construct, as we said, vector spaces can be generalized to many dimensions. Okay. You do not need to look only at 2D or 3D vector spaces, you can look at you can look at many different dimensions. So we already saw 4D, for example, you can go 4D, 5D and so on. Okay. Now, you can also go to a different type of vector space, which is called the infinite dimensional vector space. Vector spaces. Okay. For example, I will just give one example of an infinite dimensional vector space. So if you take function of one variable. Okay. So, for example, I say f of x. Okay. Now, so f of x is a function of one variable. Now, you consider the set of all possible functions of one variable. Okay. So, you are taking the set and let me denote by curly braces. So, this set f of x of all possible functions of a single variable x, and let us say for convenience that x is a real number, it does not matter. So, if you take the set of all possible functions of one variable, that means this you can easily show that this is a vector space. Okay. And why is it a vector space? Because you add any two functions, you will get a third function, which is also a function of one variable. If you multiply a function of one variable by a scalar, you will get another function of one variable. Okay. And clearly 0 is also a function of one variable, is a constant function. You can have 0, which is a constant function of one variable. You can have a negative of a function, which is the additive inverse of the function. So, clearly the set of all possible functions of one variable is a vector space. Okay. It satisfies all the necessary conditions to form a vector space. So, you can think of functions as vectors. So, each function can be thought of as a vector. Okay. This is a very important idea, and it is actually central to all of quantum mechanics. Okay. Now, each function can be thought of as a vector. Okay. Now, what you can do something else, you can ask suppose you had f1 of x and f2 of x. Suppose you had two functions, you, as I said, you can think of them as two vectors or two vectors. Now, you can ask a question, are these two vectors linearly independent? So, when are f1 of x and f2 of x linearly independent? Okay. And in this case, the answer is that if you take C1 f1 of x plus C2 f2 of x equal to 0, and you say that C1 and C2 are both are not equal to 0, are not both 0. Okay. And so, for some, so they are linearly independent if C1 f1 of x plus C2 f2 of x equal to 0 only for C1 equal to C2 equal to 0. So, if this condition is only satisfied when C1 equal to C2 equal to 0, then you say the vectors are linearly independent. If this is satisfied for some C1 and C2 which are both not 0, then I can write f1 of x equal to minus C2 by C1 f2 of x, or I can write f1 of x as a scalar. So, minus C2 by C1 is a scalar. So, I can write it as a as a scalar multiple of f 2. That means, f 1 of x. So, if linearly dependent, okay, then we can write this form, and then f 1 of x is proportional to f 2 of x. So, two functions are linearly dependent only if one is proportional to the other. Okay, so, any two functions that are not proportional to each other will be linearly independent. Okay. And this obviously implies that the number of basis functions, number of linearly independent functions is infinite. You can have infinitely many functions that are not proportional to each other. In fact, I can take any two functions and multiply them, and I will get a function that is not proportional to either of them. Okay. So, basically what I want to emphasize is that this set of all possible functions is an infinite dimensional space. So, this is an infinite dimensional vector space. Okay. And so we can see this space of functions as an infinite dimensional space. You need not you can construct several other different infinite dimensional vector spaces, which I will not get into. Okay. But let me just conclude this lecture by mentioning that you can also define inner products on space of functions. Okay. So, one example, this is an example. So, suppose you had f 1 of x and f 2 of x. Okay. These are functions, okay. They are inner product. Okay. I will just write it as f 1 comma f 2. Okay. So, these are vectors. Okay. We think of them as vectors. Okay. So, you may define them in this form: integral f 1 of x f 2 of x dx over whatever the range of x is. So, if x goes from minus infinity to plus infinity, it goes over that range. So, over the entire range of x, this would be a valid definition of inner product, because clearly f 1 comma f 2 equal to f 2 comma f 1 and f 1 comma f 1 is greater than or equal to 0, because f 1 comma f 1 will give you f 1 square, and f 1 a square of any number has to be greater than or equal to 0. Okay. And so, the integral of a square of a number of a function has to be greater than or equal to 0. Okay. So, you can also define inner product on these infinite dimensional spaces. Okay. And again such inner products are things that you will see very regularly in quantum mechanics. Okay. And what I have tried to show you in the first two lectures, okay, through this idea of linear independence and basis, is that you can generalize the concept of vectors to greater than 2 or 3 dimensions. You can in fact go to infinite dimensions. You can look at spaces of functions, okay, and you can look at all kinds of spaces. Okay. So, just to conclude, let me mention that suppose you take a function sine of x and cosine of x. These are linearly independent. Similarly, if you take sine of x and x sine of x. Okay. So, this x sine of x is another function. These are also linearly independent. You can take x and x square. These are also linearly independent. Okay. But you can take something like sine x and let us say 5 times sine x. These are not linearly independent. Okay. Because So, the only functions that are linearly dependent are those which are related to each other by a constant. So, if you take the ratio of them, you should get a constant, okay, which is independent of x. Only those functions are linearly independent, and this clearly shows that the space of functions is infinite dimensional. You can have infinitely many functions that are linearly independent. So, your basis set has infinitely many vectors. Okay. So, in the next class we will go to other things you can do with vectors. Okay. We will go to vector differentiation and functions of vectors and so on.